So we are going over the first worksheet here. So first thing is I want to verify whether what's given is a solution of the original differential equation or not. So you want to figure out the derivatives and then plug things back in, see if the left and right side actually match with each other to get an identity. So the first thing is y1 prime is supposed to be 4, and well, y1 is given here, so y1 double prime is supposed to be 0. The left-hand side of the differential equation, which said y double prime minus y prime, so you end up with -4, which is exactly the same as right side of the differential equation. So you can draw the conclusion the left and right side match with each other, so y1 is a solution of the differential equation, which is y double prime minus y prime equals -4. So I want to do the same thing. So y2 prime is c1 times e to the x, and y2 double prime is again c1 times e to the x, because e to the x has a derivative just like itself. The left-hand side of the differential equation says y2 double prime, which is this, minus y1 prime, which is still that. So I end up with 0. It does not equal to the right-hand side, so y2 is not a solution of y double prime minus y prime equals -4, but you may have already noticed y2 solves what? It solves a relatively similar differential equation, which is y double prime minus y0 minus y prime, which equals 0. Okay, that's something pretty interesting. And let's look at the third case. I have y3 prime, which is c1 e to the x plus 4, and y3 double prime, which is c1 e to the x. Therefore, y3 double prime minus y3 prime is supposed to be c1 e to the x minus c1 e to the x plus 4. So there's a cancellation. You end up with -4, which is your left-hand side. Maybe I should have written left-hand side to begin with. So my left-hand side is -4, which is the same as my right-hand side. So I have y3 is a solution of the differential equation given in that structure. Maybe you have already realized your y1, your y2, put them together, you would have your y3. So this is actually a pretty interesting observation that you have a solution of a differential equation. You have a solution of a slightly modified version of the same differential equation. The only thing changed is some constant into 0. So by adding the two pieces together, what you end up with is a solution of the original function again. So that's something that's quite interesting. This is called superposition, and it only works for linear differential equation. We will spend more time talking about it a little bit later. So along the same line of thinking, I want to verify something, the solution of the differential equation. So I want to do the same trick. My left-hand side is to take derivative of y prime. So I have t to the 6 divided by 36 and takes the derivative. So this is what I end up with, which is 1/6 t to the 5. The right side of my differential equation is t squared times t to the 6 over 36, and I take square root, and in this case, for simplicity purpose, I'm only keeping the positive piece, and clearly they are the same thing. Since left and right side equals to each other, and all I need to do is make sure the initial condition actually makes sense. So what I end up with is y of 0. If I plug in t, I realize it's 0 cubed over 36, which is 0. So yes, y equals t to the 6 over 36 solves my differential equation problem. If I were to mark it at a star, it solved that particular problem. I did have two parts here. I said there's another thing that also solves my differential equation. So my left-hand side of it, which is 0 takes derivative, is 0. My right-hand side, which is t squared times 0 to the power of 1/2, which is 0. So clearly they are the same, and you have your solution being 0, so it doesn't really matter what you plug in, your function is always having a value of 0. So clearly y equals 0 solves or is a solution of that. So what you end up with, you have a differential equation. Technically, it has two formats of the solution. So it's not necessarily a fixed solution, right? That's something that's pretty interesting. You have more than one solution here. They are not necessarily unique. Okay, so the next thing we are going to talk about is how do we do classification. Usually we classify it from 3 different point of view, right? We said it in class already. What I mentioned here is I want you to be able to name the special term that leads you to the conclusion. So the first problem we have here is second order, quite obvious, and it is nonlinear. And it is an ordinary differential equation. I call it second order because of the term y double prime. I call it nonlinear because of the term of 2y squared. The next thing we have is clearly first order. I should have said the order. And then it is linear, and it is an ordinary differential equation. It is first order because the phi y prime, the term y prime, tells me it's a first order differential equation having y times t, because t is an independent variable, y is a dependent variable. When we talk about linear or nonlinear, I'm only talks about in terms of the dependent variable. So every single term you observe here, that's related to either y or y prime. They were all linear, okay? So it's a linear ordinary differential equation. And for the next case, we have first order, right? And I have it as linear, and I have it an ordinary differential equation because the only term you observe in terms of derivative is cosine x times y prime. If you were able to use prime, it means you are not taking partial derivative. It's definitely an ordinary differential equation. If I'm talking about partial differential equation, I must have the partial derivatives, where even though actually I had a typo here, so I should be having the same independent variable here. So the next problem we have here, clearly I have 2 of order 1, so it's still first order differential equation. I claim this is linear. We're going to clarify it a little bit. And because I'm taking derivative with respect to 2 different variables, that's quite obvious. It's a partial differential equation. I call it linear, even I have x times t, because both of which they were independent variables. So having something that's nonlinear, it doesn't really matter. I don't care. It's first order because of those 2 terms up there. They were both the first derivative, order derivative. So the last problem I have here is relatively long. You may pause the video and read through it. Basically, I'm asking you to do the same thing. I'm asking you to solve a differential equation and subject to certain type of initial condition. Technically, this is an initial value problem that's coming from calculus 1, so you should be able to solve it. If you don't quite like the structure, you could have phrased it as y prime equals negative 1 over rc times y, where negative 1 over rc is a constant. If it makes you slightly more comfortable, you can imagine the problem to be something like this, and you try to solve it. So it's quite obvious for something that looks like that, the solution is going to be c times e to the power of negative 1/3 times t, if you can recall your calculus 1. So by observing something's derivative is itself with some kind of constant in front of it, it's quite obvious you can directly get the structure of a solution to be some kind of constant, e to the power of, maybe I should rename my constant because c is already used. So it's some kind of constant, e to the power of negative 1 rc times t, where t is my dependent variable. Well, my bad. I should have called it e because that's my original variable. And the problem says e of 4, which, by the way, according to the solution, it should look like this. It's supposed to be called e naught. Therefore, a is e to the positive power of 4 over rc times e naught. So my final solution, et, is e to the power of 4 over rc times e0 times e to the power of negative t over rc. You could leave it like this, or you can simplify it a little bit further by combining the exponent together. So this is what I end up with. Bottom line, what you should have realized yourself is for the differential equation y prime equals a times y, some kind of constant times y, the solution of the differential equation should have the structure as c times e to the at. You can verify it yourself very quickly. Basically, it's a derivative of a function matches itself. The only special case is the exponential function with base e.